This is a lecture about data representations. In this lecture, we're going to talk about how numbers are stored on your computer. You may be used to talking about things like integers and floating point numbers, and we're going to get into what those numbers actually mean and how they're stored on your computer, how you can write them into a binary string, how you can get them back, and then we'll drill just a little deeper than that and talk about fixed point arithmetic, which is an extension of integer arithmetic on computers, and is very useful once you start getting into digital signal processing. So let's begin with how information is represented on a computer. At the most basic level, as you probably know, everything on a computer is either a 0 or a 1. It's a binary number, and we often call a binary digit a bit, and bit is actually just a contraction of binary digit. And we have collections of bits in a row that have to represent everything that you have on a computer. Another common unit that these bits come in are 8 bits together are called a byte. And you'll often hear memory and data storage on your computer, your hard drives, your RAM, things like that, referred to in bytes. So suppose we wanted to represent a number with just ones and zeros. So if you can only have two digits, a 0 and a 1, then you can't use a base 10 counting system like we do normally, where you may count 1, 2, 3, and on up to 9, and then you move into you start using the tens digit, and you put a 0 in the ones digit. So this is a base 10 counting system that we usually use. When we're talking about using only zeros and ones, then we need to move to a base 2 counting system. So in base 2, you start counting 0, 1, and then 2, that digit does not exist anymore. So now you have to move and use a 2's digit, use another digit together. So this is the 2's place and the 1's place. So that's 2, 3, 4, 5, 6, and 7. And of course you go on and on in this. So this is the base 2 counting system. And the reason it's called base 2 is because if you have some number of places here that can hold numbers, and here's your decimal point or binary point if you're going to use base 2, then this digit here in all base systems is the ones place right here. And that represents whatever your base is. If your base is b, it's b to the 0 power, and anything to the 0 power is 1. The next digit over is the, well, in our base system, it's the tens system. It's whatever your base is to the first power. So in a base 10 system, this is the tens digit. In a base 2 system, this is the 2's digit. Similarly, this next one is your base to the second power. So it's 100 in base 10, or it's 4 in base 2. And it goes on and on this way. And so typical integers represented on a computer, so these are integers. If we don't worry about negative numbers or fractional numbers or anything like that right now, if we just worry about positive integers, then they'll be represented in as we just described, so that they'll be in base 2, and they'll have some number of bits dedicated to them, and you just count through them, and anything that is not used, anything up above here, just contains a 0. So how many bits are typically in an integer depends actually on what computer you're working on. It used to be very common for there to be 32-bit integers that were used, and it's increasingly common these days to have 64-bit integers on your computer. And it should also be known that in some programming languages, integers, especially ones with large numbers of bits, are sometimes also called longs, which means long integers. Alright, so we were just talking about integers, and I've gone ahead and moved our little placeholding diagram over here. And we talked about integers that were strictly positive, which another name for that is unsigned. But we know definitely on a computer that not all integers are unsigned. We can represent negative numbers, for example. So how is that done? One way you might think of is called a sign magnitude. So in sign magnitude, you would represent the magnitude of your number with these digits, some number that you've allocated to it. And then you add one more bit. So this would be a 1-bit that you tag on, say, to the front of it that indicates whether it's a plus or minus number. And we use this a lot when we're actually just writing integers out, right? If we say this is -3 or +10, what we've done is we've used a little placeholder, a little digit, to hold either a plus or a minus. And so similarly, we could do that. We could signify that there's some bit over here that can be plus or minus to indicate whether a number is positive or negative. Unfortunately, there are some drawbacks to this system. This is a very straightforward system, but one of the drawbacks is if you have a circuit in your computer whose job it is to add numbers together, it needs to do something different if you have a plus sign or if you have a minus sign up here. So you actually would have to have two different circuits, one that adds numbers and one that subtracts numbers. So this system is not in widespread usage, and I only mentioned it because it's a very intuitive way to represent negative numbers. Another way to represent negative numbers that was used somewhat historically, but it isn't used anymore, is called ones complement. We'll discuss ones complement because it leads naturally to twos complement, which is the most widespread way to represent signed numbers. In a ones complement, so positive numbers are done as unsigned, and negative numbers, you invert every bit. So under this system, if you had 4 digits, and if we wanted to represent 1, we would write 0, 0, 0, 1. And if we wanted to write -1, we would invert that bitwise. So a 0 would become a 1, and a 1 would become a 0. So this is +1, and this would be -1. And under this system, if you add numbers together, you actually don't need to know, you can just look at the bits to know how to add them together. You don't need to know whether it was a positive or negative number. And you also, similar to the sign magnitude system, you reserve this top bit for holding essentially the sign. If this were an unsigned number, this would be a 0 in the 1's place, a 1 in the 2's place, a 1 in the 4's place, and a 1 in the 8's place. So this would be 14 in unsigned, or it would be -1 as a signed number. And this illustrates generally that that bits floating around by themselves don't have an inherent meaning, that you need to have a system for interpreting those bits to understand what that number represents. But the nice thing is, if you have an unsigned adder and you added 14 and 1, you would add these two numbers together and it would end up being 1, 1, 1, 1, which is 15 if you added them up as unsigned numbers. If you added them up as signed numbers, you could still add it just the way that we did. It just turns out that this number, if you add them as unsigned numbers, also represents -0. So you say, well, why did you say negative 0 and not positive 0? But remember I said that if the top digit is a 1 in this ones complement system, it still means it's a negative number. But when you have a negative number and you want to figure out what was the rest of it, the positive equivalent, you invert every digit. So it's 0, 0, 0, 0, which is obviously 0. So this is a negative 0, which is the correct answer if you add positive 1 and negative 1. So one of the advantages of this ones complement system is that you can add numbers together and figure out later whether they were unsigned numbers or signed numbers. The adder still gave you the right answer. It was just a matter of interpreting the results correctly. And we've also illustrated one of the major shortcomings of ones complement arithmetic, which is that we have 1, 1, 1, 1 is equal to negative 0, and 0, 0, 0, 0 is equal to positive 0. So there are two representations of 0 in the ones complement system. And that's not ideal, and that is the major shortcoming of ones complement and why twos complement arithmetic was invented. And this is the system that's most widely used today. So in twos complement arithmetic, it's almost like ones complement, but the process for getting a negative number is instead of just strictly inverting bitwise, we say if it's a negative, you invert bitwise and then you add 1. So let's see how this works. If we have, again, 4-bit numbers, and we write 0001, that is equal to positive 1. And if we want to make a negative 1, we invert that, so 1, 1, 1, 0, and then we add 1 to it. So we get 1, 1, 1, 1. And under this system, that is what is called negative 1. So, so we have negative 1, and if we added negative 1 and 1, same as we did over here, then what we end up in this case is adding 0, 0, 0, 1 to 1, 1, 1, 1. And we get 0, 0, 0, 0. And then we have to carry a 1 off the end here. But we're only adding 4-bit numbers. We don't have a 5th bit. In fact, twos complement takes advantage of that wraparound explicitly, and it just drops off that last digit. It does not allocate a new bit for it. It just lets it fall on the floor, and you end up with all zeros. So here we added positive 1 and negative 1, and we ended up with a number which is clearly 0, just like it should be. And another nice thing is what happens if you invert 0 in the twos complement system? Well, if you want to invert 0, so that is 0, if you invert it, then you end up with 1, 1, 1, 1. You add 1. We just did this over here. 1, 1, 1, 1 plus 1 is all zeros. So that is our negative 0. But there's only one representation for 0. And that's one of the major advantages of twos complement. So twos complement has the advantage that it represents both positive and negative numbers. You can read the first digit to know whether it's a positive or negative number, just like sign magnitude. You don't need separate circuits to add positive and negative numbers. And there's only one representation for 0. So twos complement is kind of the ideal system, and it's the one that's most widely used.